Okay, hello everybody. I'm Vero Estrada-Galinanes. I'm associate professor at University of Stavanger. Racin is a PhD student from the same university. Today we talk about when Merkle met Entanglements. In this talk I will talk about redundancy in peer-to-peer systems, about our collaboration with Swan, and the prototype that Racin is working on, user-side redundancy, and then the impact of redundancy on Merkle risk. So, our motivation is to store a document for long term in a decentralized system. Do you think you can recover a file after a decade or more with current redundant mechanisms? It's a bit of a challenge. So, this is Swan. There's many cute bees or Swan nodes. And but these bees may decide to be free at some point, and some may fail or disappear, and so it's a failure. The failure happens. So, what happens if you have your file in that node that just suddenly disappear? You will be very sorry for that. So, I will talk about three different approaches to achieve redundancy in a peer-to-peer systems. Basically, they are like well-known mantras somehow. I call it the more the better and the less the better. And then I will talk about my work. This was developed during my PhD, Entanglements codes. Okay, so let's go to replication. Replication is very easy, just copy the file. It's straightforward, but it has expensive space requirements because you need to copy the whole file. And it's not good for long-term storage, especially because, for instance, in Swan, when you are syncing the files, or in any peer-to-peer network, when you are copying blocks, you are copying blocks that are popular. But in long-term storage or something that is a document that is your personal document, nobody cares. And okay, yeah, you can incentivize, but still you need some redundant method that is appropriate for long-term storage. So here is a block that is missing. So then in this way, with replication, basically you have two different, with free copies, you have two different more ways to recover the file. And when you distribute this file and these free replicas, yeah, okay, there's some nodes that participate in this, and when one node disappears, so this node can give you the file that is missing without any decoding, without any repairs, just straightforward. In erasure coding, I will talk about M out of N blocks. What does it mean? So basically you have the file, and instead of just storing the file, you split the file in blocks, in M blocks, and with some magic based off arithmetics of doing the Galois fields, you create more redundancy. With this redundancy, you can save, with this approach, you can save space requirements, but this is very expensive with repairs and with the maintenance in the system because you always need to read M blocks to recover the file. And so, okay, again, you have some parallel, some other ways to recover the file, but these are involve many blocks. And here, in this case, we distribute the blocks. So instead of the original replica that we have in replication, we split in 4 fragments. We generate some redundancy, so there are like more peers involved in the repairs. And you see that if one node is missing, yeah, you have to find 4 other peers that are available to recover the file. You can increase, so in this previous example, you can tolerate up to 3 failures. Then how do you increase the fault tolerance? Okay, you can subdivide these initial fragments, and then you generate more redundant fragments. And but in this case, we are with the same space overhead, and now there are more nodes involved. But the problem is that we are also increasing the number of peers that need to be available to do the repair. And this is a problem in peer-to-peer networks, or for instance, if the system is under attack, or if they have low availability, this node. So this is not good. So what happened with entanglements? Entanglements, the main idea is that you mix the file with other files in the system, or you mix the blocks of your file with other blocks of your file. And how do we do it? With this is based on a XOR operation, so it's much cheaper operation than the Galois fields. And it's very simple, like is XORing to your block with alpha other blocks, and that will generate alpha blocks. But because this is part of a system that is all entangled together, then you can use other blocks out of these alpha and alpha other blocks that can be used during the repairs. So the good thing about alpha entanglements is that repair cost is constant, no matter the alpha that you use. You will always need 2 blocks for repairing one single fail. And the storage overhead is equivalent to the alpha blocks that you're generating. And fault tolerance grows exponentially with these alpha blocks, because now when the block is missing, you will have this path of 2 blocks, or this path of 2 blocks, actually alpha path of this, but then you will have more and more as a larger path to recover the block if there is a big failure that is affecting the system. Racin will talk about entanglements first. So in this case, now we have an equivalent block that is equivalent to the replication. And now if the block is missing because the PR is not there, so we will use only 2 nodes. And you see now that we have blue that are the direct blocks that were generated during the entanglement. But there are also many other blocks that were already stored in the system, or they were stored later in the system, that can be used during this repair process. So that increases the number of peers that can participate during repairs and the possibilities, and like we are distributing more the information. And that's actually good. And also, if we want to increase even more the involvement of the peers in the system, we can, instead of using these sites, we can use a small block so that we split the original block in 4 fragments, and then in this way we are using the same space of overhead as the previous example, but now we are basically distributing the file in many more peers, and then the repairs can be parallelized better, can be done in a more efficient way. So in a nutshell, so here are replicas. Replicas you always need, so like peer availability requirement is something that is not good, so replicas are the best because it's just one peer that you need. In entanglements you always need 2 peers for doing the repairs. And in the traditional erasure cost, it depends, but is M. But we can also, as I showed in the previous slides, we can increase the block distribution in the large number of peers, which is something positive. But in the case of erasure codes, in this way, growing in this way requires more storage overhead. And but with entanglements, yeah, we can use small blocks and without increasing this storage overhead. And yeah, Racin will talk about this demo.
So I will go through the prototype very briefly, and then show you a demo of the repair algorithm, and show some results. So in a nutshell, this is how the traditional or file offloading to Swarm is now. The entire file is sent to some Swarm node. It might be your own Swarm node, and then you this chunks the file into 4K, and the file is synced across the network. So what we did in our prototype is that we implemented an additional layer in Go, which splits the file into 4K and adds the encoded blocks according to the redundancy scheme. Then this is sent to the Swarm node in the same way and synced across the network. But in the once the nodes receive the file chunk, the user gets back the manifest hash, which it keeps in a collection, because this collection is then used when the user wants to restore the file, because it has the information about what is the data, and what is the parities. So I will show you the demo here. See. So this shows all the data blocks in the whole file, so total 115 data blocks. And then the coloring down here means the red ones will be unavailable, and unavailable means that it could not retrieve the file within 1 second. So it doesn't distinguish what kind of failure. It says if we cannot get the data within 1 second, it's a failure. Then the blue ones, it's repaired, and green is downloaded. So it starts off by this coloring curve. And as you can see, there's some which is already red, but when it goes to number 59, so this is event 459, it requests a parity block for number 25, which we will use to repair later on. But also what can happen is that the parity can also fail. So the algorithm keeps running, and on number 41, you see that the one block is data block is repaired using these two parities on the side. And then if we go to 160, yeah, so here you have a case where there's two parities after each other which is failed. And what the algorithm does here, it first repairs the parity which is further away, and now it can repair the one it needs. And then now it has the sufficient information to repair the data block. And this keeps running until all of the blocks are either green or blue. And then it terminates. So, to go back to the presentation here, we also have done some evaluations, and here we inserted errors of 5 and 15%, and we used one prototype with entanglement codes and one prototype with Reed-Solomon. And again, it's this 1 second failure that if you cannot retrieve the block within 1 second, it's a failure. This is what we simulate there. So this is the results for a file of 1 megabyte. And as you can see, for the baseline swarm, the entanglements codes are performing better there. And we believe that this is because we are only connecting to one single swarm node when we are retrieving the file, and then this has some limit on concurrency. But with our prototype, we are sort of overloading this concurrency limit because we are issuing all of the requests in parallel. And the results with the Reed-Solomon, they are also not too good, because this is like we need to do some more work on the implementation there. And we also think this will be more reduced if we ran the swarm nodes ourselves. Locally, yeah. But the main takeaway here is that we can implement user-side redundancy, and even with relatively high amounts of failure, it doesn't have any cost in the download time.
So next step, system-side redundancy. So what happens if we move redundancy to the network, to the system? What we are interested in now is how these Merkle trees are affected also with redundancy. And so then, when you have, if you are storing data off-chain, like if you use Swan to store data off-chain, usually you can create a Merkle tree and then include the root of the Merkle tree in the blockchain or in Ethereum. So here we have the data block at the leaves of the tree, and all these other blocks are basically hashes blocks. So, and this is interesting because we can do an efficient content verification. Also, if we want to know that this block is part of this market tree, this block is part of the file that I want to download, so I need to only verify with some more blocks, hash blocks from the Merkle tree. But how this Merkle tree is modified when we introduce redundancy? So well, when we are using replicas, this basically is not modified because unless we are inserting some tag or some label to this replica, I mean the replica is identical, so we have exact hashes and the root will be exact. So no modification. When we are using erasure codes, basically the Merkle tree grows to all directions because first we will have more leaves because we will have the encoded blocks. And then we will have more hashes, and then basically it also increases in height. And there are also some other challenges that we have seen in previous implementations in Tahoe and also in the Devcon when they are using erasure codes that need to be careful because there are some kind of attacks that you can, like for instance, include a second file here in the codes, and they will have the same root. So it's no time to discuss this. Anyway, with entangled blocks, the thing is that because in the way that the process is done, the coding is done, basically we are creating a kind of a chain of entangled blocks, and this chain is basically if you XOR every 2 consecutive blocks, these 2 consecutive blocks will represent exactly the original data block. So as you see, like in this case, the first one is equivalent to this one, but this one can be regenerated with 2 blocks, and this one with these 2, and this one exactly. And we have actually multiple layers that you can do like this. So basically, you can play in the implementation so to avoid modifying the Merkle tree, but because of this property of the entanglement. We didn't go more further than this, but we are thinking in this for previous implementation, for next implementations. So concluding remarks, Swarm's ambitions to provide long-term storage, so it needs to combine different redundancy methods to provide the service, to provide different service. And at the moment, it only adds replication at the syncing process, and it's considering implementing the erasure coding and entanglements. So towards this goal, we show how can we add entanglements at the user side, and we show some measurements about this, and then we expect to continue with this work and apply entanglements after fixing it inside the node. So that's all for today. Yes.
Any questions? Please.
So could we go back to the slide with the Merkle tree?
Yeah.
So the green blocks, the green chunks,
Yes.
which form the Merkle tree,
These ones.
yeah, those ones. Are they in any way protected against loss? Because they are just regular. Like the swarm network does not distinguish between blue and green chunks. It doesn't know which one is green, which one is blue. A chunk is a chunk.
Yes.
So are you considering some redundancy for the green ones as well?
Yeah, that's what we discussed when we went to Madrid to the Swan Summit, that we could also include made entanglements at this size, but we are actually at the moment we are not sure if that will be necessary. I mean, the storage, extra storage overhead for doing this entanglement, adding the redundancy here, it will be not much, but it adds complexity to do this, no? And but on the other side, because these are well protected, you can regenerate all this because basically this is the hash. So if you can recover this because you have a very high fault tolerance here.
No, you can't, because
you can't find them.
That's how you retrieve a file. You basically start unpack it from the entire package tree.
Well,
But
if
if
it is,
you have the lowest layer, you can go up.
Well, they're
But you
saying
don't
if
have
you
it.
ask for, you're just asking for a hash, they don't know how to regenerate. They don't know which nodes it takes to regenerate it. If you just ask for, like, hey, give me this hash and it's missing.
You access the file from the root hash. That's how you need to unpackage them. You retrieve the top chunk with the root hash.
yeah, that's
Address.
that's true. I mean, for locality, you access from here, and yeah, my talk here focus actually on the verification of this, of if this block belongs to a certain file or. But if it is for locality,
Oh, I see, I see.
you really need to add this extra redundancy.
We are running already late, so let's go for the last question.
Yeah, so I just kind of assume that the context of entanglement as to like what can be entangled with what is like, it's assumed to be like application specific and not necessarily like a global.
It depends on how do you implement. One way could be like the node that uploads the content just has in memory some last, like for instance with this example that we did, is like 15 blocks in memory and keeps doing the entanglement with these last blocks and
Yeah.
keeps always in, yeah.
So
That's
it's
one way. The second way will be if you want to entangle with blocks that are in the system, then you need to download like free blocks for it. Or you can keep it like you maybe you don't need to download if you have a pool of like blocks that you were already syncing before and reuse this pool to do the entanglement, and automatically you are entangle your file with other blocks in the system.
Yeah, so I guess my question is if like I'm a node on this network, am I going to know the context of the entanglements of what I'm storing, or will I just not know?
Well, this can be encrypted. This is, you don't know, is that what you're asking? Or,
Kind of.
Did you?
yeah, we can discuss.
It's
Oh,
okay.
it's okay.
Yeah.
Follow.
Yeah.
We are running. Thank you so much again.
Thank you.